Afternoon. Welcome, everyone. So today we are absolutely delighted to have Professor Siamak Ravanbakhsh giving our colloquium today. So Siamak got his start at Sharif University, so he's a computer scientist, but I know from Siamak telling stories that he actually considered switching to physics at some point. Yeah. We got talked out of that by a computer science professor.
By a physics professor. Actually.
By a physics professor, okay. Well, that's kind of weird. Anyway, after undergrad, Siamak came over to Canada, where he was a graduate student, got his PhD at the University of Alberta, where he also worked in what used to be called the Alberta Ingenuity Center for Machine Learning, now has been renamed AMI. And then after that, went on to Carnegie Mellon University, working as a postdoc in the machine learning department, but also started really collaborating with a lot of people in the McGill Center for Cosmology, and got more and more into applying machine learning to astrophysics. And a few years ago, Siamak started a faculty position at UBC until we were lucky enough to snag him here, bring him to Montreal, where he's now a professor both at McGill Computer Science and also at Mila, where he also holds a CFAR AI chair. So Siamak loves applying machine learning to all sorts of interesting problems in physics, as well as doing more machine learning, pure research, and recently has just really gotten into this idea of exploring the role of invariants and symmetries in deep learning. As you can imagine, that's also a very powerful thing in physics. So welcome. And so today, Siamak's going to tell us about explorations in machine learning for astrophysics. So take it away.
Thank you very much, Adrian. Thank you. So is this working? Is it good?
Yes, it should be working.
Yes? All right. So my clicker is not working, so I'm going to use this, see if it works. Okay, yeah. So I'll be talking about machine learning applications for astrophysics. These are sort of applications that I've been working on over the past few years. The outline of the talk is as follows. So I don't assume a lot of background in machine learning or deep learning. So I'll give a quick 2-slide background on or maybe 1 slide on machine learning and deep learning, and then I'll tell you about how we can use different data structures very briefly. And then I'll just go through several examples where there are we consider this 2-dimensional space of machine learning tasks and data structures, where I pick some task in machine learning that is being applied to a specific data structure in astrophysics. This way, you'll also get an idea of how we can apply ML methods and what are the range of problems that we can probably approach using machine learning. And then in the end, I'll discuss some interesting directions and challenges for future research, future application, both of machine learning and also advancing machine learning techniques to be able to apply them to some astro data.
So if you feel comfortable, you're welcome.
Oh, right, yes. Thank you. Much better. Okay, so for people who don't know what machine learning and deep learning is and what it has to do with AI. So AI is the broader field. It is about intelligent agents, but machine learning is a subfield that focuses on agents that learn from the data. So there is some learning involved. And deep learning is a sub area in machine learning that works with methods, with a specific set of methods and models that have certain characteristics. There, for example, you have these hierarchical and deep architectures that learn more and more abstract and complex representations of the data. The models are massively parameterized, and they're usually parallelizable, and we can do GPU computation. Maybe the font is too small. Okay, so deep learning in one slide. So in machine learning, we have, let's see. In machine learning, we usually have some model, f of w here. W is a set of parameters for that model. And we have some data. And we try to fit the model to the data by minimizing some cost function L, right? We find a set of parameters w that best fit the model to the data. Oh, it works. So in deep learning, the model usually has many layers. And now you'll see what this means. An example, a canonical example of this is a multi-layer perceptron, where this is the model. We have the input. What we do is that the model can be written as follows. We have the linear transformation of the data followed by some nonlinear function that is applied element-wise, and we just repeat this. We apply another linear transformation followed by a nonlinear transformation. These linear transformations are called the weights. These are learnable parameters of this model. But the nonlinearity is fixed. Okay, so the reason that we have the nonlinearity is because if we didn't, then the entire thing would be just a composition of linear functions. It would be linear. It wouldn't be able to express a lot of, it wouldn't be able to express the nonlinearity that we see in our data. But due to these nonlinearities, you can show that even if you have just two layers here, you can approximate any continuous function over bounded domains to an arbitrary amount of accuracy using this model, using multi-layer perceptron. So it is very powerful. Now, okay, so we have the model. How do we actually fit it to the data? The way that deep models usually work is that we use gradient descent. We start from some random assignment to the weights here, and oh, it's dying. And we do gradient. We move in the direction of the opposite direction of the gradient to minimize the loss. And while these gradients are calculated often, because it's difficult, the architecture could be quite complicated. These are calculated very efficiently using automatic differentiation. And these gradient estimates are also not obtained on the entire data set, but on a small subset of the data set. So we get noisy estimates of the gradient. And that's it. So this is how we do deep learning, right? Well, at least in one slide. Now, okay. Now we want to apply these to astrophysics. There are very different types of data structures we have in astrophysics. We have the image data. We have, graphs. If you look at the cosmic web, for example, as a graph, you have the point cloud structure. If you look at, for example, stars and galaxies as points in a 3D space, you have the volumetric representation if you're looking at some density field or vector field, and you have the spherical form of the data. And then, well, the question is, how do we apply the model that we just saw, which is a canonical model, canonical deep model, to this sort of data structures, right? So the short answer is that a general way to do this would be through the symmetry transformations, symmetries corresponding to these data structures. So this is related to what I do for my research, and I'll just revisit this idea a couple of times, but I don't go into much details. So in the 2D images, for example, we have translation, rotation, and reflection symmetry. It's usually translation that is used in deep models. In point cloud data, we have permutation symmetry. We can just shuffle the points around. The order doesn't matter. There is no inherent order in these points. And there's also Euclidean isometries. I can move things around, rotate, etc. For spherical data, we have the rotation and reflection symmetries of the sphere. Like these are the 3D rotations, right? So these symmetry transformations gives us ways to design models that can operate on these data. Basically, we're gonna modify the model that you just saw, the multi-layer perceptron, to make it work with these symmetries. So the way we do it is that we want to learn a model. This is so unreliable. I want to learn a model that knows about these set of symmetry transformations. These could be translations, rotations, etc. If you take the input and you transform it using one of these transformations, and then you apply your function, your model, your deep model, you get something, right? Well, you can also first apply the model and then transform the output of your model. We then say that this model knows about symmetry transformations if this diagram commutes. That is, if what we get going through the blue route is equal to what we get if we go through the other route. So this imposes a constraint on F. And this is called equivariance constraint. It's sort of a generalization of invariance to a set of transformations. And if the model is equivariant to a set of transformations, and these transformations are related to our data structure, then the model could be applied to that data structure. Okay, let's see an example. Well, first, this constraint is on the entire model, is on the entire deep model, right, over here. But it's sufficient to apply this constraint to only one layer. If it's true for one layer, it's going to be true for the entire deep model. And so that layer, remember, the layer is just a linear transformation followed by element-wise nonlinear transformation. So let's look at one example. So suppose we're looking at 1D translations. And this is our input, is a vector of length 5. And the output is also a vector of length 5. And we are multiplying this input by this matrix, by this W matrix here, to get the output. And then we're applying the nonlinearity sigma here. So what we are saying, what the equivariance constraint here says, is that if I translate my input by any value, by any amount, my output should be translated. It's basically what this is saying. My output should be translated by the same value. And if you impose that constraint for all possible translations, you'll see that this matrix W should have a particular form, should have this form. And these colors, what they mean is that all the elements of the same color should take the same value. Okay? Well, this matrix is actually doing 1D convolution operation. And so you can extend this idea to 2D and 3D for 2D and 3D translations. And what you get is that this feed-forward layer that we saw here should be doing a convolution operation. That is, you should take your input, you should apply a convolution filter, and now you need to learn. So the learnable parameter is this convolution filter that you're applying to the image. And this gives us convolutional neural networks. So these are a set of neural networks that are applied across a lot of different domains to analyze image data. So it's all derived from this simple multi-layer perceptron through symmetry principles. So what we could do is that now we take these convolutional neural network and apply it to astrophysics problems. Okay? So this is our 2D space of data structure and task. And the first application we're looking at is estimating cosmological parameters. We're applying the regression task, and we're applying it to volumetric data where we have translation, 3D translation, basically. So this is one slide, introduction to cosmology. This is probably more than I know. But so you guys know more about this. But anyway, I'm going to do it. So the standard model in cosmology is this lambda CDM model, which means we have dark energy and dark matter. And we have a matter density given by this omega m, and then the density of dark energy is given by omega lambda. And the universe, there was a Big Bang. The universe is expanding, and this expansion factor is changing over time. And the way it's changing depends on these physical constants, like the Hubble constant and these two constants that we just saw. So it is important to be able to estimate these constants accurately, right? And we don't know these constants as well as we know the speed of light, probably, right? So another sort of, for someone who's coming from outside to this area, another important thing to note in cosmology is that, well, first, since there is an expansion here, the light is redshifted, and there is a relationship between the amount of redshift and this expansion at the time the light was emitted. So there is this equivalence between the amount of redshift, the age of the light source that we're looking at, our distance from it, and the size of the universe at the time. Oops, what happened? Okay. All right, so we want to estimate these cosmological parameters. There's a traditional way of doing this. Which looks at the two-point correlation of mass density. So it looks at all the pairs of points across the universe, and then you look at, for different distances, how much correlation is between the math. And then you guys do Fourier transform. You get the power spectrum. And there is now analytical models that relates the power spectrum to those physical constant. And based on the values that you calculate from the power spectrum, you can try to estimate what is the amount of, for example, dark matter in the universe. But this approach is making a lot of simplifying assumptions. It's basically two-point correlation is only sufficient in statistics if you have a Gaussian random field, and higher order statistics are sort of ignored in this approach. So what we decided to do way back in 2016 was to use deep models for this purpose. So instead of directly estimating these parameters, we tried to learn to estimate these parameters from the data. So we generated a lot of simulations and tried to feed that to a neural network to basically predict these cosmological parameters. So these are the simulations we generated. You see that they are produced using different value of these cosmological parameters, and they are fed to a 3D convolutional neural network that you know about. And it turns out that the model now can predict these cosmological parameters better than the traditional approach. So this is these are the estimates given by the power spectrum analysis, and the crosses are the ones given by the comet. So since then, there have been follow-up work significantly improving these results. Now we can actually make these predictions even more accurately. Okay, so second example. We're looking at a task which is a structured prediction, and it's done on volumetric data. Okay, the same sort of data structure. Instead of predicting a single number that was a cosmological parameter, now we're trying to predict the next step when you're simulating a system, right? Okay, what do we do? So the first idea is to just take the initial, yes?
Is it okay to ask questions?
Yes, go ahead.
So, in your previous slide, 3 slides ago, you had axes prediction and ground truth.
Yeah, that's
Do you
right.
actually know what those mean?
Oh, okay. So because these are simulations, we know the ground truth of the value of, for example, sigma 8 or omega m. And then a perfect prediction would produce values that are on the diagonal.
Right. So are you saying that all of the crosses are systematically underestimating?
So crosses, well, there is a bias for sure, but crosses are generally better, especially for omega m, than power spectrum analysis, and you can calculate basically the loss. This estimate was even with the same architecture was significantly improved. Somebody just reran our code, and they saw even, I think, order of magnitude better results using the same code. I don't know how we messed that up, but in any case, this is still better than what you get. So it is.
Is there a measure of how much better? How many deviations, or is there?
Yes, I'm sure we had a measure. I just don't remember it exactly right now. Yes.
Okay.
So it is for sigma 8. It is not actually, maybe not much more, but for omega m, it is more evident. But again, we can do this much better now. At the time, there wasn't even like a 3D convolution. There was no code for it, so we had to do a lot of hacks to get it right. Okay, so structured prediction, we were talking about doing simulations. So the first idea is to start from this perturbed grid, where you have particles on different points in your 3D grid, and try to predict, based on this initial perturbations, where the particles will end up at, redshift 0 at the current time step. What would the largest scale structure of the universe look like? So this is embodied simulations in the context of cosmology. So we can try to directly predict the density field. This didn't work well. So the reason is that the network really doesn't see where each particle is going. It just sees where they were, what was the original density, maybe perturbed, and then what was the final density. A better setup would be to predict the displacement field, which tells you where each particle is going, basically, on the original grid. So instead of predicting this density field, you predict the vector field. So this turned out to work actually well. So we have a deep model that takes as input this perturbed grid that shows an initial perturbation of the particles and tries to predict what would be the density field after the evolution of the system. This is telling us how the universe is evolving. Even better than that was to try a simpler model, a physics-based model, in this case a first-order approximation that just tries to evolve the system by moving the particles linearly in the direction of original velocity, and then try to use a deep model to correct that prediction. So takes the first-order approximation, the deep model tries to correct the predictions of the simple model. This is an idea that could be applied generally in application of deep learning to simulations, where you have a simple prediction that then you can try to correct it rather than directly using deep models to make predictions. So this worked pretty well. Again, we trained this deep model on 10,000 simulation this time with a fixed set of cosmological parameters here. And what I'm showing you here is the error in prediction from different approaches. This is if we just use the original linear approximation. The length of these vectors is showing you the error in the prediction of particle that is started there. The error in the prediction of its displacement field. This is the second order Lagrangian perturbation theory. This is what people used in cosmology. And this is the deep model. Basically, the error is very small compared to other methods. So it's making a better prediction. And what was surprising here was that once the model was trained, we applied it to setups where these cosmological parameters were changed significantly. For AS, it was actually changed by almost an order of magnitude, and still we were able to get good generalization. That is, the model still was making good prediction for these different set of parameters that it hadn't seen during training. Okay, so that's the second one. Now we're moving to more interesting data structures. So we want to look at point sets. We want to see how we can use these predictions for point sets for galaxy cluster. You can think of a cluster as a set of points, set of galaxies, right? And try to make predictions for them. So point clouds. They don't just have applications in cosmology. In cosmology and astronomy, yes, you have point clouds. You have galaxies or stars appearing as points in a three-dimensional space. But they also have applications in other areas, in autonomous vehicles, in geographical surveys. In your iPhone, they have now LiDAR sensors that are actually similar in technology that is used for these point clouds. We produce lots of point clouds from different fields. So it's good to be able to make prediction with this type of data. What are the symmetries? We have the permutation symmetry. So if I give you a point cloud, if I give you a set of 3D coordinates for these points, in addition, I could give you other things. I could tell you, for example, what is the luminosity of this star, and so on. But at least I'm going to give you 3D coordinates. It doesn't matter what order I present this to you, right? You can shuffle things around. It's the same data set. So you have permutation symmetry. You also have Euclidean symmetry. So because it's a Euclidean space, things could translate and rotate. That's an additional structure that we could use. So first we see how we can handle permutation symmetry in these data sets. Again, let's go back to our original perceptron model, multi-layer perceptron, and we're just looking at this one layer, right? And remember that we wanted this diagram commute for this layer. So in this case, for any permutation of input, we want the output to have the exact same permutation. If you apply this constraint, the feed-forward layer can only look like this. So you would have only two untied parameters, on the diagonal and off diagonal. And it doesn't matter how big is your set, you only get two parameters. But it turns out that if you actually use multiple copies of this, you can create more parameters even for a single layer, and then you're stacking them to build a deep model. You can show that you get universal approximation of functions over sets. That is, this architecture now can approximate any function over set if we use this type of symmetry-based model. Okay. So what we tried was that at the time we applied it to point cloud data coming from, this is a data set of objects. We wanted to see what the model is learning. This only knows about the permutation symmetry, right? And we saw that it's in the first layer, the model is learning very simple features that are local. It's learning about points being present in some region of the space. In the second layer, it starts to detect more nonlinear features and surfaces. So even just accounting for permutation symmetry helps in building deep models that can analyze point cloud data. But then there has been a lot of work since then on analysis of point cloud. People have been looking into also bringing in the Euclidean symmetry. We have done work that combines the Euclidean symmetry with this, and now the goal has been to be able to apply this to very large point clouds. But I'm not going to talk about that here. So what we wanted to do was wanted to apply this to application in astrophysics, right? So this is one small application that we considered. So we have this red mapper catalog. This is a set of 20-something thousand galaxies. There are galaxy clusters that have between 30 to 300 galaxies in them. This image is not from this data set. It was a nice image, so I put it there. For the galaxies in there, we have photometric readings. So for all of the galaxies. But for some of the galaxies, we have also a spectroscopy. For a small portion, we have more accurate measurements. And from these spectroscopy, we can predict the redshift, the distance of that galaxy very accurately. But in addition, we have this clustering information, right? We have the cluster structure. So what we did was that, noting that, okay, if we have clustering information, we have a set structure. That is, if I permute the input properties, the output prediction of the redshift should be also permuted. We built this symmetry-based deep model to predict the distance of these galaxies from the photometric readings, and we were able to improve the predictions that were in the original data, and was basically given using domain knowledge. Yeah, so there are a lot of more opportunities for applying these models of point clouds in cosmology and in astronomy. This was, unfortunately, we haven't done enough, so this was the only example I could find. But still, I think it demonstrates the point that these models can have can give improvement even where you have some other domain knowledge that can help you in your prediction. Okay, so another task now. Now looking at generative modeling. So this is a different task. It's not simply prediction of some label or some structured data. Generative modeling is about learning densities. So I give you a lot of examples and you want to learn the density. You want to learn the distribution of the data from those examples. If you've seen these images of deep learning being used to produce fake face images, that's an application of generative modeling, basically. You're learning the distribution of all the face images, and now you're able to predict, you sample a new face image from that distribution. Okay, so I have totally lost track. Did I start at 3:30?
Mm-hmm.
Okay, good. So the application we're looking at is at weak lensing, weak gravitational lensing. So we have a foreground math that's distorting the background light source. And there are these weak lensing methods that try to basically quantify this foreground mass, but they will need data for calibration. They need galaxy images, basically. It's these galaxies that appear in the background. And for that, there have been methods that produce galaxy images using these parametric models. So this is a real galaxy. This is what is produced using a parametric model. But these parametric models are not good for generating realistic images for irregular galaxies. So what we did was to use deep models to generate galaxy images. The idea is to learn this density, which is parameterized again by a W, by a set of parameters. We're able to learn a distribution over galaxy images conditioned on some properties. For example, do you want a distribution over elliptical galaxies? Do you want it to have this particular luminosity and so on? Conditioned on some properties, we want to be able to learn to generate galaxy images. Usually these generative models look like this. So you give the property that you want and some random noise, and you send that through a deep model, and you get a galaxy image at the output. Okay, so this, by changing the random noise, you get a different shaped galaxy. So that's how you're representing this density. The way that this is learned, however, is very different. There are very different models to learn this neural network, and they might impose additional constraint on this structure. Now, when we applied it to Galaxy Zoo data, we got this type of result. So this, what you're seeing here is pairs of galaxies. One of them is real. The bottom ones are real. So bottom one here, here, and here. And the top ones are generated, conditioned on the same set of properties. So in this case, we have 27, 28 binary features. For example, does it have a satellite or not? And we're conditioning on that. We're generating galaxy images. So you see the type of images that are being produced. Sort of, they look similar in terms of the properties. But then we were more interested in distant galaxies, right? Because they appear in the background in weak lensing. So in a more recent work, we looked at Cosmos data set. So there are 85,000 galaxies that are, pictures are produced from the Hubble Space Telescope. These are the real images. And this is what we get if we use deep models. But then what we did was we integrated the pointer spread function of the, so basically these are the nuisance effect that we're getting due to telescope optics, atmospheric perturbations, etc. We can bring that into the generative process so that those are integrated in the learning process, so that we are actually generating these noisy versions rather than these smooth versions that better resemble the actual, the same set of samples that we're getting from in the Cosmos dataset. In both cases, so the samples in one column have the same redshift, luminosity, and size. So they're conditioned on these properties. Okay. And then we looked at, this is very qualitative, just looking at the pictures. We also look at the statistics of these, morphological statistics of these galaxies. For example, the morphological statistics might look at the brightest pixels, 20% brightest pixels in the image of the galaxy, and look at the distribution of that, the variance between those, look at the distance between those brightest pixels, see what area they cover, etc. This gives us, for example, M20 statistics, or there's the Gini statistics. These are sort of made up statistics by statisticians to measure something about the morphology of the galaxy. And in terms of so these are histograms then. They're looking into two-dimensional of two statistics, and we see that the generated galaxy images have the same sort of distribution in terms of these statistics to the real data when compared to the parametric fit. The parametric fit being the old way of doing things, basically fitting a disk to the data. So we're getting fairly good distribution of galaxies producing the data like this. Okay, so moving to a different data structure, this is spherical data. Okay, so when I look at example application in regression and structured prediction. Okay, so spherical data, motivation, they're all over the place also. Well, not as much maybe as point clouds, but they have applications in astronomy. They're also in earth sciences. When you want to look at the surface of the earth, you want to make weather predictions, or climate, for climate science. Being able to analyze spherical data is also very important. And also in 360-degree cameras, you produce also signal that's sitting on a sphere. In particular, in astronomy, different modalities of the data could sit on a surface of a sphere. In particular, the example that I see a lot is the CMB, cosmic microwave background. So what do we do? For some reason, in astrophysics, people use the Hillpix convention for pixelizing the surface of the sphere. I'm not sure why. If you look at the Hillpix is produced by pixelizing this polyhedron. It's called rhombic dodecahedron. It's not symmetric. It's basically, in a sense, that it's not vertex transitive. You can't move this vertex, for example, to this vertex, because this vertex is adjacent to 4 edges. This one is adjacent to 3 edges. So it's not completely symmetric object. A better choice would have been any of the Platonic solids. So Platonic solids are face, vertex, and edge transitive, meaning that you can map all the edges to all the other edges and so on. And these are the only solids that have this property. And the way you pixelize them is that you take just one face, you break it into smaller faces, and you project them out to the surface of the sphere. And then you, again, repeat that successively, and you get very close to something that looks like a sphere. Right? This gives you a very good pixelization of the sphere. So the question is now, how do we apply deep models to this? We've seen that in order to apply deep learning, we need to work with the symmetries of that data structure, right? For a sphere, we have the rotational symmetry of the sphere, which is a nice group. If you look at these Platonic solids, they also have their own symmetries that is a subgroup of the rotations. Certain rotations are allowed. But then once you start pixelizing, what happens is that the pixelization does not refine that original symmetry. Meaning that if you look at these pixelizations, there is no way for you to move the red dot to the blue dot. It's not a very obvious point. Meaning that by pixelizing more and more, we're not getting closer to the rotational symmetry SO3 of the sphere. We're just stuck with the original symmetry of this shape. Okay? And this causes a problem. Now we have to solve this in order to be able to apply deep models. So what I'll do is that I'll give 3 different approximations to the symmetry of the sphere, and then I'm not going to go into details of how we design models for those approximations, but then you'll see how they perform, okay, in practice. So we're going to approximate the symmetries of these pixelized spheres. So the first approximation, we're going to use a hierarchy of symmetries. We already have a method that would allow us to design these feed-forward equivariant maps if we have a hierarchy of symmetries. So in this case, the hierarchy looks like this. We have a set of faces, and each face has a translation and rotation symmetry. So again, this is an approximation of the symmetry of a sphere. It's a very crude approximation. It's saying that I'm going to break this up into these faces. Each face can be rotated and translated. Okay? It's hierarchy because we have the permutation symmetry at the top, and then we have translation and rotation symmetry for each face in a hierarchy. So we can build a model for this approximation. But this is not really good enough, because why consider all the possible shuffling of the faces where the only shuffling of the faces that are allowed are given to you by the rotations? So then maybe only consider the shuffling of the faces that are produced by the rotation of the sphere. Okay? So the set structure is not good enough. The set structure says everything could be permuted. We are saying no, don't allow permutation of everything, just do permutations that correspond to rotations of this solid. But again, this can be improved. One problem with this approximation is that we are saying, yes, you can rotate the solid, but at the same time you can arbitrarily rotate the face. This is not good. Rotation of the face is given by the rotation of the solid, right? So then we can tie these together. It's no more going to be a real hierarchy, because the rotation at the top layer, for the faces, is dictating the rotation of each face as well. But still, we're able to design, equivariant models for this. So we're getting successively better, getting closer to the actual symmetry of the pixelized sphere through these ideas, and then we can apply them to actually see how they work in practice. So this is a synthetic data set of digits. What we have done is that we've projected the digits to the surface of the sphere. Now there are different pixelization of tetrahedron, cube, octahedron, and icosahedron. And for each of them, we try deep models that are produced using different symmetry assumption. Symmetry assumption type 1, type 2, and type 3. And we see that as we improve our symmetry approximation, we bring it closer to that of the sphere, the accuracy of the model also improves, right? So how does this perform in real-world setting? We applied this to 360 camera images. The standard task there is segmentation. Yes?
Can
Yeah, good observation. Yes, the reason is that the face is a pentagon, and then once we do the pixelization, there's going to be a technical problem. Once we do a pixelization of that face, we can't just allow, you pixelize it by these triangles, and then these triangles cannot be moved to each other by just translation. You have to do a flip as well. And that's just too much of a hassle to handle. So we didn't do that shape. Okay, so application to 360 degree cameras, segmentation, we get significant improvement over state-of-the-art, previous state-of-the-art using this approach. It's also very fast, so you can apply it to really large, high-resolution images. Applied also to climate data. Again, we got sort of significant improvement over the prior work. This bottom is a cube model, basically pixelization that we get using the cube. And then we wanted to apply it to CMB, but we didn't. So what I'm showing you here is from previous work when we wanted to apply deep models to CMB, but there was no model that would work on a sphere. So this was 2018. There was one model. There was the spherical CNN. It wouldn't. We tried it. It wouldn't scale. It was very slow. It wasn't running on the spherical signal. So what we did instead, we did projections close to the equator, so that we're getting sort of flat images, and use those small images. Use a set of small images to make the prediction of the cosmological parameter. Here again, we're given the CMB. We're trying to predict the underlying cosmological parameters corresponding to that CMB. There are different tasks you can look at. You could look at, for example, denoising of the CMB, or in this case, this was a simpler and more obvious task. And at the time, even this approach worked well. So again, we have the ground truth and the predictions we're getting, and we were getting good predictions. So I don't know how much motivation we have right now to apply the spherical model, but that's something probably somebody should do. Okay. All right. So let's see, how much time do I have? I have time, right?
10 minutes.
Okay, good. Anomaly detection. So again, different task. Looking at strong lens finding. So there are different ways of doing anomaly detection. Some are supervised. You have supervised methods, semi-supervised, unsupervised method. Here we're looking at supervised method. So we have some labels that are telling us this event that you're seeing in your data set is anomalous. It's a rare event. Try to find events like this. So it's like classification, except that it's highly unbalanced data. The events that you're looking for are really rare, so you don't have a lot of labels for that type of data. Example of that is detecting a strong lens, strong lensing. So again, we trained model on simulated data, similar to LSS, what you get from LSST. And what we found that, yes, using deep models, deep image-based models, deep COMNETs, you can make really good predictions. The quality of your prediction, so this is a false positive rate, true positive rate. You get the ROC curve, and the quality, the accuracy of predicting these would depend on the signal to noise ratio and the Einstein radius, basically, of the strong lens. You probably know more about that than I do. So here are images. What would a true positive versus false positive look like? These are the true positives. These are the lenses that were found by the network in the data. And these are false negatives. So these were not detected. There is lensing happening here, apparently, but the network did not identify these. There's also unsupervised anomaly detection, which is much more challenging task, which is much more interesting. And it's very important in astrophysics because this could give us a way to identify new phenomena, right? If there is something happening in your data set that is an anomaly, that is an interesting observation to look at. But again, that's the problem there because you have to be able to define what is anomaly and what is not anomaly. So this is something we haven't done anything for. This is something we want to work with Adrian and Caitlin. We're looking, for example, at applications to Gaia dataset. That's going to be at using point cloud or poinsettia structure for unsupervised anomaly detection. Okay, so with that, I'm going to quickly talk about some interesting areas for in machine learning that could have high impact in astrophysics if we make progress. So this sort of would be these are areas where we would need more research on the ML side to be able to address problems in astrophysics side. So one is interpretability. It depends on how you define science, right? If I am able to make good predictions, is that good enough, or do you need a formula? Like if I have a model, it's predicting how the universe would evolve, it's making good prediction, it actually matches the observations, but it's a really huge network. Is that good enough for you as science or not? So if we need to go and look into the model to understand what it's doing, or if we want to distill that information into simple formula, then we need better research. I mean, there are work in symbolic regression where you produce a formula. There is work in network distillation when you learn a big deep model and then try to distill all the information in a smaller model. There's the standard sort of way to do for interpretability, at least in medical domain, is saliency maps, where you try to come up with ways to identify what in the image caused that particular prediction, but these are not good enough. There's also the problem of domain transfer, where what we can do with this is that in most of the examples that I showed you were on simulated data, right? But in the end, we want to take these models and apply them to the real world data. They won't transfer. If you just take that deep model and apply it to real world images or density fields, it just doesn't work, because even if it has slightly different statistics, it usually causes problem. So we need ways to be able to transfer the models across domains. Even if it is not, from simulation to real, it could be that you're looking at different instruments and you like to be able to transfer the data from one instrument to the other or across different modalities. There are some work in domain transfer in machine learning and computer vision. It would be interesting to do more in astrophysics. For example, this image is showing how people try to train a model on video games because there you have control. You can say where you want to go, but the images that are produced are pretty realistic. Then the other important challenge is handling massive instances. So right now, deep models are good at working with big data, but the big data usually means you have lots of data. So you have lots of images, but each one of them is reasonable size. So how can you design deep models that can take in huge instances that may not even fit in the memory, right? How can you process these in a reasonable way? Well, one idea is to just break things up, but take, for example, the simulation task, where you want to look at the effect of gravity. If you're dividing things up into chunks, you're looking at just one chunk. You're not seeing the effect of gravity coming from objects that are far away, right? So that's not generally a good solution. And we don't have a solution here in deep learning for handling such massive data sets. And the other one is something that I already pointed out, better unsupervised anomaly detection methods, or at least more principled ways of finding anomalies in an unsupervised way. A lot of the news that you hear in astrophysics is about surprising things that people have noticed. These are all anomalies, right? And what are good ways to go about defining these anomalies and then automating their finding, given that they could have very different, they could be produced, they could have very different natures. The one way that you may define anomaly could be very different than what people have, some other group have looked at the data and have found anomalies in the data set. Okay, so with that, thank you very much. And I also want to thank all my collaborators. I just was too lazy to put all the names here. There were so many different papers that I talked about. If there are any questions, I'll be happy to answer.
If there are any questions, I can also bring a mic around so that it's captured in recording. Any questions? Oh. Okay, here first, then I'll go.
Nice talk. So
Thank you.
You discussed about permutation symmetry, and especially when you're using galaxy clusters, as well in your classification. I think your redshift estimation. I think this project. I'm sort of wondering what advantage we get by introducing that. If I compare it with currently available machine learning redshift estimation methods.
So yes, so we did compare it to that. So what you could do is that you can apply just your ordinary machine learning method on individual galaxies, right? Don't look at the clustering information. You get some accuracy. And the way you can estimate the accuracy of your model is that you have this held out set where you have accurate estimates of the redshift from a spectroscopy. You say, I'm not going to include that in my training data. I'm going to go back and see what sort of predictions I'm making for that data just using a spectroscopy, just using photometric information, and see how close I am to what I get using a spectroscopy, right? So we have a way to validate the model. And we can then now try to train the model without using the clustering information, without bringing in the zeta structure, but just looking at individual galaxy. You get some accuracy. You look at the zeta structure, you get better accuracy.
Yeah, I was just wondering that whether you compared with currently available or sort of very popular neural network models that people, astronomers, generally use to estimate photometric redshifts for galaxies.
So the value that we looked at was sort of normalized redshift estimate. I don't remember exactly the name, but we looked at the best estimate that was given for RedMapper dataset, and we improved that basically on their specific held out set. If that's what you mean, that's what you mean. You're saying that there is this specific method that people are using to get redshift estimates.
Quantify this thing, comparing with, for example, NZPy and EasyPy and all these softwares and see whether.
So this was not using a particular software that what we compared with, but it was basically people who curated the data set. They did all sort of analysis to, in the end, give estimates for all the galaxies in their data set. And they had an error measure comparing different methods and their best method, and we were improving that best method that they had. So I'm not sure what software or what sort of data they incorporated to get their estimates.
I think there was someone here.
So my question was, how is fixing non-linearity adequate in the deep learning model? And this is very general, but...
So how, sorry, say that again.
So how would fixing some degree of non-linearity be adequate to, I guess, predict...
To make good predictions?
Yes, to make good predictions.
Well, there are different ways I can answer that. So first, you need nonlinearity, right? There's no okay.
Yeah, that's good.
So then, what nonlinearity to use? So the one that I showed you was really nonlinear. It's this squash, the logistic function.
Yeah.
But what people use these days is more linear than that. It's called ReLU. That is used more often. It's basically just it's piecewise linear. It has two pieces. So it's the only part that is not linear is just one point. Basically, it changes direction. But that's even enough to basically build models that are highly expressive, because you can show that. So even if there was no learning, so you can think of the model with two layers. As first, you're learning some set of features, and then you're making prediction based on these features, right? You can assume that you don't even learn those features. Those features are fixed. But if you have enough of those features, you can show that you can approximate any function up to an arbitrary accuracy, any linear function, any continuous function up to an arbitrary accuracy over a bounded domain. So, so the fact that you can actually learn those features is just going to be a plus. So that's one way of answering your question, that you don't even need learning of the features to be able to claim that you can build expressive models. But with the learning, that's enough. Now, I don't know, you're looking for some sort of intuition about how the nonlinearity kicks in?
Yeah, pretty much. Because, yes, you can approximate a lot of functions, a lot of nice functions linearly to a certain degree, and you'll get most of the behavior to whatever order you're looking at, and that's fine. You can approximate it any order. You can approximate a lot of things linearly if they're nice enough. But so then why? I guess I'm not really sure why there's even a nonlinearity considered, or what that adds, or.
So the nonlinearity would. So you would need it first, because otherwise you just get a linear function. If you stack a bunch of linear maps, you're going to get a linear map, right?
Linear. Yeah, that's good.
But so you need a nonlinearity. But then the type of approximation guarantees that you have are as follows. It's the L infinity norm. So you're basically saying that if there is this function, I'm going to be able to build another function that's pretty close to this, such in a sense that the biggest distance that they're going to have over this bounded domain is going to be less than epsilon.
Sure.
And for that, you're going to need, n hidden units, meaning that you're going to need at least n neurons in your second layer. So, so the approximability is in that sense, which is a strong sense. You're getting as close as you want, right? Everywhere.
Sure. All right.
But I think in the end, I didn't quite get what was bothering you, but I'll be happy to chat afterwards.
Other questions? Anyone else have questions? Yes.
Hi. So this might be a dumb question, but when you were talking about the permutations and how you were saying that the data sets were equivalent, so say you have like a 2D matrix of intensities, which you basically have, or in a sense.
For which application are we talking about?
Say it's the like the two-dimensional map or two-dimensional image of your galaxies, and you were to permute the data points, and you said it was the same data set, but then how would you extract?
Not for that data set. For that data set, that's image. For image, you can't just permute the pixels. You'll get a completely
It's only
garbage
for the
image.
point set data.
So this is for the point. Yeah, whenever you have a set of objects, each of them coming with their own features, you can permute them. So if you could have a set of images, for example, and you want to make a prediction for a set of images, you give me a set of images from galaxies in the same cluster, and you want from that image from the set of images to make predictions. You don't really care which image goes first, which image goes second, right? So you can permute the images, but you're not, for the image itself, you have translation symmetry. So you can translate things, or at least in theory, the symmetries of the image grid is translation symmetry.
But with any
but
given
it's not
image,
permutation.
you can't switch around the points.
You can't shuffle
because you
them.
would lose spatial.
Exactly, and that's how, from this fact, the fact that what sort of transformation is going to destroy your data, you get the symmetries of the data structure that you're working with.
Thank you.
Okay, I think we're at time now, so let's thank Siamak again. And we'll see you next week.